Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 12, Gravitation, Video 3. Today's topic is gravitational potential energy. The objectives are: no gravity is a conservative force, hence work done by gravity doesn't depend on the path. To understand, gravitational energy is relative, only delta U matters. To understand that gravitational energy is a shared property of the body and Earth, and be able to use and interpret a generalized expression for gravitational potential energy. So in Chapter 7, we have learned gravitational potential energy on Earth's surface when gravity is constant. So when gravity is constant, the work done by gravity equals to force times the displacement. So you start from 1, you worked to 2. So that's a displacement from 1 to 2. Gravity equals mgy1 minus mgy2. So gravitational potential energy is defined as mgy. So ended up with work done by gravity equals to mgy1 minus mgy2, or negative change of gravitational potential energy. So let's take a look at this diagram. So when the object is falling, gravity weight does positive work. So your potential energy actually decrease. So work equals a negative change in potential energy. As the body moves upward, your weight does negative work. As a result, your potential energy increase. So this value is true, this expression is true regardless if the body moves up or down. Work done by gravity is always equals to change in potential energy. Negative change in potential energy. Now let's take a look at gravitational potential energy generalization. So we have just learned Fg is not a constant. As you move away from Earth, Fg is a function of the distance. So now let's take a look. How do we find the work done by gravity? The work done is a dot product. Remember, force is a vector, so is dr is a vector. And force is toward Earth, dr is away from the Earth. So the angle between them is 180 degrees. So we have to use Fg times dr times cosine 180. Cosine 180 is -1, so that becomes negative Fg times dr. Fg is gmem over r squared, so you have a negative sign times dr. And this gives you, from your reference table, equals to gmem over R2, the top, minus gmem over R1. So remember, gravity equals the change in potential energy. That means it's negative of U2 minus U1, so that gives you negative U2 plus U1. So that gives us the expression U actually equals negative gmem over R. This is a general expression for gravitational potential energy. Do not confuse gravitational force and gravitational potential energy, even though this two looks very similar. Force is proportional to r squared, but well, energy is proportional to r, and the gravitational potential energy is negative, while force is positive. Gravitational potential energy is conservative. So that means it does not depend on the path. If you move this way from R1 to R2, you will have the same gravitational energy change. It doesn't matter which way you're moving. So the work done by gravity depends only on the initial and the final position of R, does not depend on the path. So the work done by gravity is the same, and because your change of gravitational potential energy is the same. That change does not depend on the path. Let's take a look at this graph, gravitational potential energy graph. Gravitational potential energy, U equals a negative gmem over R. So the graph looks like this. It's negative, it's always below R, right? As R approaches to infinity, U approaches to 0. So U is always negative, but it becomes less negative with increasing radial distance R. Gravitational potential energy depends on the distance r between the body of mass and the center of the Earth. Note that we have chosen U equals to 0 at r equals infinity. That because why is that? Because that is convenient for us to have this expression. We can choose our u equals to 0 on Earth's surface. That will make the u expression more complicated. However, because only delta U is significant, so remember gravitational potential energy is relative. So we want to choose a point 0 most convenient for us. So in this case, at r equals infinity, u equals 0 is most convenient for us. That's why we choose that point. Let's take a look at this example from the Earth to the Moon. In Jules Verne's 1865 story with this title, 3 men were sent to the moon in a shell fired from the giant cannon sunk in the earth in Florida. So RE equals to 6,380 kilometers and ME is 5.97 times 10 to the 24 kilograms. Find the muzzle speed needed to shoot the shell straight up to a height above Earth equals to Earth radius. So in this case, the only force is gravity, so total mechanical energy is conserved. So K1 plus U1 equals K2 plus U2. So at point 1, you'll have kinetic energy 1/2 mv1 squared plus the U1 is negative gmem over re. At a point 2, your kinetic energy becomes 0 because that's the bare minimum. You shoot 2.2 when you are all out of kinetic energy. And its gravitational potential energy is negative gmem over 2re. So from this expression, you can solve for V1. V1 equals gme over re. Substitute all the numbers and you'll have 7,900 meters per second. That is the muzzle speed to shoot the shell straight up at 1 radius above Earth's surface. Now, what is the escape speed? That is the muzzle speed that would allow the shell to escape from Earth's completely neglect air resistance, the Earth's rotation, and the gravitational pull of the moon. So again, total mechanical energy is conserved. K1 plus U1 equals K2 plus U2. But escape out of Earth's atmosphere, what does that mean? That means K2 equals to 0, also U2 equals to 0. So when you set that equals to 0, you can solve for V1. That becomes 2 times G times ME over RE. Seems like double of that speed. That gives you 1.12 times 10 to the 4 meters per second. So here, this is actually called escape speed, is 2 gme over re. So it doesn't really matter what is the mass you are trying to escape. So it has nothing to do with the mass of escaping object. It's just anything escape have the same velocity. 2 times g is constant, mass of the Earth is constant, and radius of Earth is constant. All objects have the same escape speed. We can use the general expression U equals to G m, big M times little m over r squared. On Earth's surface is still mgh. Let's see. So G, U at re on the surface of the Earth is this, negative gmem over re. And at a little height above the Earth's surface, the U is this, gmem over re plus delta H. So change of U equals to U2 minus U1. U2 is this, and U1 is this. This is a fraction. We have to add fractions. To add fractions, you need a common denominator. We multiply the two together. So you multiply the first term by re on the bottom, on top. You multiply the re plus delta H on the bottom and on top. Then you add it together. This is what you'll have, the expression. Now let's examine the one on the bottom. Since re is much, much, much greater than delta H, so re squared plus re times delta H, this term is approximately equals to re because delta H is so small. So that simplifies delta U becomes the bottom becomes re squared, then the top is delta H. So this term in front, that is actually G. G equals to Capital G, the gravitational constant, times the mass of the Earth over RE squared. So therefore, delta U equals to mg delta H. So we have derived this expression is just a special case of the general expression. Test your understanding. Is it possible for a planet to have the same surface gravity as Earth, that is, the same value of g at the surface, and yet have a greater escape speed? Now let's look at escape speed expression is 2gme over re. So what is the g? G at e, g of e equals to gme over re squared. So that's times re on the bottom and times re on top. So what do we get is v1 is just becomes 2g times re. So g can be the same, but if this r increases, then v would increase. So is it possible? Yes, it is possible. It is possible if the radius of the planet rp is greater than the radius of re. That's it for today. Thanks for watching. See you next time.